we have discussed about various conductors both of ACSR type, that is aluminum conductors, which has applications for high voltage transmission, and also we have discussed about the recent advances in the conductor technology, particularly the high temperature low sag conductors. In brief, now we will focus on the design considerations particularly, and also for the selection of the uprating or upgradation of the existing transmission lines. How this new conductor are beneficial, or how are they economical, and how can they be used for the higher rating or uprating of the existing transmission towers. So, this in detail we will focus on the new type of conductors which have been used in the country, and several of the projects are being executed and some have already been executed and they are in workings presently. So, we look into the important design considerations about the new conductors which are being used for uprating or upgradation of the existing transmission lines. So, there we have known that a remarkable growth, particularly in the Indian power system in the recent year, about a decade. So, in terms of voltage levels, the country is already operating the lines at 765 kV AC and 800 kV HVDC lines, and mentioned earlier in the lectures 1200 kV experimentation line is already in progress. So, with the ever growing right of way, which is a very important aspect to be considered for the design of towers for UHV transmission, and available site constraints require sustainable development, particularly in the transmission system in our country. So, with the introduction of the new and latest technologies for the higher voltage transmission systems in the country, there is a quantum reduction in the newer towers which have been designed, particularly the right of way has been reduced and the requirement per megawatt of power transferred with the bulk power transmission lines operating at very high voltage and ultra high voltage transmission. So, the enhancement pertaining to the capacity of the existing transmission lines could be done by either uprating the existing or newer type of conductors which are available, that is the high temperature low sag conductors, which we briefly discussed how these conductors could be used for the uprating or upgradation of the existing transmission lines. We will focus into this aspect, and also the adoption of multi circuit towers, particularly in the forest areas and where the right of way is a constraint. In such places, the use of high temperature low sag conductors are being used to particularly reduce the resources, the efforts, and also the economical cost pertaining to the transmission lines. So, we will discuss we will discuss about the conventional conductor initially, then we will be moving on to the high temperature low sag or high temperature high current conductors. So, the conventional ACSR, that is aluminum conductor steel reinforced, which we have discussed in the earlier lecture, is the most common conductor which is being used for the EHV, that is extra high voltage and ultra high voltage transmission lines. We know that ACSR technology is a relatively lesser technology, and its low technology and its performance is quite satisfactory, and it is being used for several decades both in the country and also in many other countries. However, normally when operated to a maximum temperature between 85 to 90 degrees, this ACSR conductors have limitations beyond 95 degrees. Here they, in case if it is operated, the sag is increased, and also in case of ACSR or any other conventional conductors, it could be AAAC, all aluminum alloy conductors, etc. The sag varies at a relatively higher proportion with temperature. So, in case the temperature exceeds more than 95, with a higher proportion the sag increases. So, this type of conductors for operational above 90 degrees cannot be adopted. So, an alternative and a newer technology is being recommended, and it is being used and being operated in the country at a very high temperatures. So, the HTLS or the high temperature low sag conductors which we have discussed, these conductors are capable of being operated continuously at a temperature of at least more than 150 degrees, minimum of 150. We have seen their performance in the laboratory up to 200 degrees. So, these conductors increase in sag particularly is not appreciable at a very high elevated temperature between 150 to 200 degrees. So, above a certain temperature which is known as a knee point temperature, all the stress of the conductor will be borne by the core, that is the characteristics of the conductor. So, the core of the conductor basically comprising of invar or a composite material has low thermal coefficient of expansion. This results in relatively low sag, because the operation of this conductor at a very high temperature because of its inherent properties having a low thermal coefficient will result in a low sag or no sag when operated at higher temperature than the conventional ACSR or AAAC conductors. Here the usage of thermal resistant alloy, that is thermal resistant alloy or fully annealed aluminum which is at 1350 degrees enable high temperature operation without loss of strength and to reduce the sag. So, the replacement of aluminum conductor with steel reinforcement or AAAC, that is all aluminum alloy conductors or other conductors in the existing transmission lines with the high temperature low sag conductors will enable to see that the higher carrying capability could be increased without any modification in the existing tower. So, this is a very important point when we are going in for the operating of the existing conductors. It is to be noted that while interchanging the conductors at a very high capability with a very high capability HTLS conductors, there is no modification in the existing towers which is required. So, we have earlier discussed about different types of HTLS conductors. We will slightly go in depth about their construction and also the details of these types of HTLS or high temperature low sag conductors. So, the first one is the invar type of conductors which is given here. This is the invar type of conductors having various thermal resistant aluminum alloy extra conductor which is shown here. Inside is a zinc coated invar alloy or aluminum clad invar alloy is present. here the construction of this conductor is similar to aluminum conductor steel reinforced conductor, and handling and stringing also is similar in the tower. So, you can see the aluminum strands which are of thermal resistant and are of aluminum alloy with a composition of a zirconium added into the aluminum alloy. So, the core of the alloy or of iron consisting of the alloy of iron and a nickel which has a low thermal coefficient of expansion. So, this is supposed to be 1/3 that of the steel in comparison to the thermal coefficient. So, it is lesser by 1/3 in comparison to the steel, galvanized or aluminum clad. So, after transition temperature, all the load, entire load is being transferred to the core, here the core of the conductor, and hence the low sag is compared to that of a aluminum conductor steel reinforced after this transition temperature. So, this is important aspect. So, as a temperature after the transition, the entire all the load is transferred to the core, that is a core which consists of aluminum clad invar alloy or a zinc coated invar alloy. This helps to see that the transition temperature is compared, when compared to the ACSR, gets reduced. This will help in reducing the sag. The second type of HTLS conductor is the aluminum conductor steel supported. So, this is the typical structure of the annealed aluminum conductors which are seen, and the central steel core with the central steel core. So, here it is a galvanized steel core with a fully annealed aluminum conductors. Depending upon the voltage or a current level, the conductor size varies. Again, this ACSS conductor is in similar to the construction of aluminum conductor steel ACSR, except here the aluminum strands which are being used are fully annealed at 1350 degrees. So, and this conductor ACSS can be operated at 200 degrees without loss of its mechanical or electrical or thermal strength. Here the steel core of the conductor, which is of very high strength, and most of the load, and hence lesser sag is noticed in comparison to the conventional ACSR conductor which operate under high temperature. Usage of aluminum conductor steels supported type also improves the conductivity by more than 63% and has a better and self damping characteristics. So, this conductor require more care during handling and also stringing because of the softer aluminum strands which are in the conductor. So, the third is the gap conductor GAP, which has a small gap. You can see the construction of the conductor here. These are the extra high tensile galvanized steel core. You have followed to that is a heat resistance grease which is surrounded that. Then the conductors of the compact size conductors are placed, and finally the round type of conductors are at the last periphery. So, you can see that high tensile strength galvanized steel core and a gap structure, and finally you see a small gap in between the conductors, where this gap structure is basically filled with heat resistant filler. So, this thermal resistant aluminum alloy and a small gap between this is a heat resistant filler, where this is maintained between the steel and aluminum. Here basically this junction is the gap here, and these conductors strung by tensioning the steel core. So, hence these have a lesser sag again in comparison to the aluminum conductor steel reinforced type. So, this conductor requires special erection techniques during stringing, particularly during stringing these require special techniques. So, the fourth is the carbon fiber composite core conductors. This is a conductor which is shown here. You can see number of conductors are arranged in such a fashion with the center being the composite core. All are annealed aluminum conductors. You can see the construction, the center being the carbonized core. This conductor sample of the conductor is also shown here, where you can see the construction. There is no gap, particularly with the conductors which are being connected at the tips, and this is the carbon core, composite core, which is replaced by the steel core for the earlier conductors which we have discussed. So, this has a special properties in comparison with the ACSR conductor, and this ACC or aluminum conductor with the composite core which is shown here, having an alloys with aluminum strands fully annealed, similar to the previous two types of composite previous high temperature conductors, but the core is made up of composite material. This could be glass fiber and carbon. So, this also possesses less sag and operates at 180 degrees and has lower coefficient of thermal expansion like the earlier high temperature conductors. But this require more care during handling and also during stringing of the line due to the softer aluminum conductors, annealed aluminum conductors at the for the conductor. So, this which has a softer aluminum strands also requires a special type of dead end clamps and joints. So, this is the requirement for this type of composite core conductors. The other type of conductor is the metal matrix composite core conductor, where you can see here the aluminum matrix with a composite core. This is the composite core with the aluminum matrix, and these conductors are all shown here with the extra thermal resistant aluminum alloy. So, the adhesive of the aluminum foil for wrapping the core is also indicated here. So, this is again a special conductor. It is similar in construction to the ACSR conductor and also similar to the ACCR conductor with the composite reinforcement which is been done. For this type of conductor, aluminum strands are again of thermal resistant like the aluminum alloy containing the zirconium in its composition. So, here the core is made up of metal matrix, that is aluminum oxide fibers. The previous is the carbon and fiberglass core. Here the metal matrix composite core consists of aluminum oxide fibers, and this type of conductor can be operated up to 200 degree centigrade. Suitable tools particularly and other accessories are to be used and recommended for this type of conductor while stringing in the transmission lines. So, there were about the 5 various types of recently advanced conductors which are being used for the upgradation or uprating of the existing transmission lines. So, we will discuss about some of the design considerations, particularly for the selection and upgradation of the existing lines. So, how the conductors while replacing could be advantageous and what are the necessary consideration design aspects to be followed. So, for the current carrying capability, we know that the temperature rise in a conductor is due to the intended maximum continuous power flow under defined ambient conditions. This should not exceed the maximum operating temperature of the conductor. So, in case of the high temperature conductors, anywhere typically between 150 to 200 degrees is the current carrying capability. Temperature thermal rise could happen, and the size and weight, the size of the conductor and the weight also be equivalent to that of the existing ACSR conductor. So, in case of the uprating of the conductor, the mechanical strength, the mechanical weight of the conductor should be similar to the previous conductor which is being replaced, and followed by that it has to have the weight of the existing conductor, and also it should be able to limit the wind load and vertical load of the existing tower when subjected to corona considerations and minimum interference requirements like RIV or the corona inception or extension voltage levels at that operating voltage as earlier which were required for the ACSR type conductors. So, the uprating or upgradation of the existing transmission lines is very important. When considerations earlier we have seen some of the considerations like the current carrying capability, the size and weight. Now, it is a sag and tension characteristics have also to be considered. So, here the maximum permissible tension to be limited to the design is the maximum tension of existing tower, which is subjected to maximum limit of 70%, and the everyday limit of 25% of the rated tensile strength of conductor to control the vibration or fatigue due to vibration or a wind aspect. So, the sag of the conductor at maximum continuous power flow is to be limited to the maximum sag of existing conductors to maintain, and also the minimum ground clearances. The fourth point being the economical analysis. Economic analysis is an important factor to be considered in the design. So, here the comparative economic evaluation of various conductor alternatives are to be verified, carried out, keeping in view the total cost of the conductor and the associated hardware or accessories, and the cost of the entire stringing and the new installation. And the important point also to be considered is the ohmic losses which could occur in various conductor alternatives corresponding to the perceived normal power flow requirements should also be properly evaluated, and suitable considerations are to be done for the economic analysis. So, when going in for a new transmission lines for a specified power transfer capability, an elaborate conductor section or a selection analysis is to be carried out to see and obtain an optimal solution. So, unlike the upgrading or uprating of the conductors, here the selection of conductor in such cases are not generally limited by the sag tension and sag consideration. So, the consideration regarding the suitability of the selected conductor to the available designs and the industry or utility practices have to be followed for the new transmission lines which are being adopted or which are going in for the HTLS conductor transmission system. So, before going in for the uprating or upgradation of the existing conductors, we will find out some important aspects how it is practically done and what is the necessity for the requirement for before actually the uprating or upgradation of the conductor is done. So, sometimes it may be necessary to construct a transmission line by tapping the existing transmission line. So, which is to feed load say for a nearby substation or any other equivalent utility. So, the tapping of this transmission is done by loop in loop out arrangement, which is known as LILO arrangement. This by providing a slack jumper conductors with the existing transmission line. So, how this arrangement is done is shown in the single line diagram here, where you can see the existing line. Here it is the existing line. So, the existing transmission line is to be connected to a proposed say substation or a feeder. So, in such case the existing line has to be properly split and it has to be terminated near the substation in this arrangement. So, the tapping of the conductor, that is a loop in and loop out arrangement, is to provide suitable jumpers with the existing transmission lines have to be carried out. So, some precautions have to be taken while going in for the tapping of any existing transmission lines. There should be a solid tee off line from the existing transmission line is not allowed under any circumstances. So, the solid tee off line from existing line is not allowed. You cannot take the connections from the existing with the solid tee off. So, tapping is done from either a B or a C type angle tower only by the loop in or loop out arrangement as indicated earlier. So, in case if there exists a suspension tower at the location where it is to see the loop in loop out arrangement is to be done, then this suspension existing tower is to be replaced by a suitable B type angle tower. So, before it is being done, a tower arrangement, necessary tower arrangement has to be made. So, then the loop in a loop out arrangement is done either by providing a double circuit towers on the proposed line or by providing a single circuit towers separately for the loop in. The next point to be considered is a dead end tower. In case the dead end tower, one circuit may be taken to the proposed substation or a feeding station at a right angle as a loop in. The other circuit may be taken out from the substation, that is a loop out, should be connected square to this dead end tower as shown. So, the one existing is loop in circuit, the other is a loop out circuit which is to be taken out from the substation. So, the tapping from the existing line is generally done by providing a slack span jumpers. So, jumper conductors of actual rating of the conductor are provided for the tapping of the existing transmission lines, which should be connected with the existing lines by means of parallel groove clamps. There is a PG clamps which are known by the utility engineers. So, these have to be employed. So, it is also advisable to provide at least 3 parallel groove clamps at each connecting point to secure the jumpers safely from better reliable conditions considerations.